Hi there. So in this video, I'm going to walk you through a process of doing time series forecasting. It's a very cool time series forecasting model by Facebook. It's called Facebook Profit. It has been around for a while, and I thought that this is actually a good time to do this video because this is still the start of the year, early stages of the year, and now is a good time to do all your forecasting and get your numbers right, your predictions right. And then you'll be able to take the right kind of decisions from a marketing operations perspective. Or if you are into data yourself, this might be already familiar to you. If not, you can use this to sort of help your predictions that are going to assist the marketing teams. So Facebook profit is one of the time series forecasting approaches, and there are some other methods like autoregressive models, in the AI group, in the AI family of models. Then there are some, neural network based or machine learning based ones as well, like LSTM. So there are multiple approaches to doing time series forecasting, but Facebook Profit is probably one of the more elegant ones among them, relatively easier to implement as well. And that's why I thought that this is the one to show. And by the way, it's free and open source to use. So, yeah, let's jump right into the Python notebook here. So you have to first get some of the important packages and libraries, pandas and NumPy, of course, the ones to do some data manipulation, do some quantitative stuff with the data. And then you have Seaborn and Matplotlib, which are for the visualizations. And then you have to, import the file within this environment, which by the way is Google Colab, which is again a free and open source one from Google. So it's interesting. One is it's a Python stuff going on within a Google environment. But anyway, so once this data set has been loaded, so I'm going to talk a little bit about the data. Now I'm going to show the top five rows, the recent five rows of the data, not the recent, but the five rows from the data. As you can see, it actually starts from this date, so it's somewhat around a couple of years of data, and or not really, less than that. And you can see it's the 5th of November when it starts from 2023, and it gives us data of revenue, channel spends, channel impressions, and also organic impressions and clicks. And yeah, that's pretty much it. So that's the data that we have here. As you can see, this has been built out in a way which is suitable for this kind of an analysis, and also some more complex analysis beyond time series as well, like say marketing mix modeling and stuff like that. So this data set has been cleaned already. So there's such a thing called exploratory data analysis or EDA, and you have to carry out EDA to make the data available, ready for analysis. So that part has actually already been done. Okay, I did not want to go into that because that was a very lengthy process sometimes, and any data science will actually tell you that it's 80% of the work, and it's not easy to get it ready for analysis. So you have to get it ready, and once that's done, this is the final format that it looks like. Even after this, there may be still room for cleaning. Okay, it's never really 100%, but that means it's somewhat there. So from this, by the way, we are only going to use one column, which is the Shopify Amazon revenue. So this is, like I said, this is real data. So this is the revenue, as you can see, point-wise data. And by the way, point-wise means here there are different dates corresponding to different dates here, but this is actually weekly data, as you can see. So 5th, 12th, 19th. So it's basically weekly data. So it's aggregated from the original data. All right. And by the way, I'm actually running it on L4. Okay, if I were to show you the runtime types, so this is actually sort of a subscribed version of Colab, but you can use CPU for this one. It does not give you, it's not going to be very resource intensive. But yeah, the point here is that that this is a weekly aggregated data, and the one which we are going to use for time series analysis in Shopify Amazon revenue, which is collection of which is like a sum total of the revenue from Shopify store backend as well as Amazon backend. And this is the weekly data for that. Okay. So then we're going to do something called a statistical test. Now, why are we doing this? So for most time series approaches, time series forecasting approaches, time series modeling, you actually require something called stationarity of data. You need to see whether data is stationary. Now, in real life situations, most data is not stationary. Okay. You'll see in this data set here, there's something called a seasonal Shopify Amazon revenue. So what does that really mean? It's a seasonality component. Okay. So it's taking a baseline and it's then multiplying it and saying that this is the multiplying factor and saying that, okay, this is this much above that level of seasonality, above that baseline. Okay. And that is the seasonality component. So basically, while doing this data cleaning, this particular data set has already had the seasonality component taken out of it, right? And that is why it is, very, and since it's been separated from it, the residuals versus seasonality, it has got that sort of stationarity element to it, although seasonality is just one component. So any time series data can actually be broken down into seasonality, trend, and the residuals. Okay, you add them back together, get the original time series data. So in order to check for stationarity means that the data, time series data, has got some statistical properties which are fixed in uh, in in time, meaning they're not time varying. So those can be like mean and variance, the statistical properties. So there are a number of statistical tests you can carry out in order to check for stationarity. And checking for stationarity is the first step. If it is non-stationary, then you have to take some other steps in order to make the data more stationary and available and ready for time series or forecasting models. Those steps could be things like transformations, again, mathematical processes, like suppose log-log transformations, for example. But you can do other transformations. Then you have to do, then you can also do differencing and differencing. That's another method to try and make the data stationary. But the first step is to actually do some statistical tests to see this data is stationary or not. So statistical tests like augmented decoupled test, ADF, and this has been carried out here and using this particular method, right, to import the necessary library from stats models. And this is inbuilt and outside of Profit. And once, so you can see it's only this column that's been applied to it. And once that's been done, you basically try to find out the result, the statistic. And this has to be as low as possible and if possible negative. As you can see, it is negative, and also the statistical significance is almost quite there, 0.05 for 95% confidence interval significance level. You would want less than 0.05 ideally. It's just a little bit above that. It's kind of there, right? And this is because, so this pretty much means what? This means that the data is relatively stationary. And this is because of the kind of work that's been already done with the data set. Okay, but in general, the data itself was quite stationary to start with to a certain extent. Now, the point here is that this is just done just to show you what is usually done in time series forecasting. The really cool thing about Facebook Profit is that you don't really require this. Okay, you don't require a stationary data necessarily in order for Facebook Profit to do well. Unlike some of the other time series forecasting approaches, like say the autoregressive models, okay, that family of AI models, those do require stationary. So now I'm going to just do a quick plot of the revenue. So you can see that this is how it looks like. It's just a plot of the revenue column itself from within the data set, and it does not have any time component within it. But it's of course time varying, we know that. And you can see there's a general trend upwards. The obvious striking thing, as you can see here, is that it drops to zero at the start and at the end. Now, this is deliberately done by me, okay, for the purpose of this analysis. The reason why I did it, I'll explain later. But the point here is that it's dropping to zero at the start and at the end. And this is happening why? This is real data itself, and this is because that's the amount of data that is available, right? So it wasn't available before that, it's not available after that. And of course, it was taken like a couple of days back only, so there wasn't any data at all. It's still getting collected. And for the date that it was collected, it was, that was the last date that the data was available for. Now, usually what you would do, not usually, I mean, you have to, properly, if you have to do it properly, you have to get rid of the data which is dropping the get rid of those rows. I did not do it on purpose. I'll just come to that in a moment. So let's now look at, some of the aspects of the data set. So we have 71 rows of data, which is to say that there are 71 weeks of data. Okay. So that's what 71 here means. Then we have, as you can see, these are all non-null, which is important. Again, this is clean data. This is not to be the case. When you work with data, if there are non-values or missing values in some rows, so there's going to be, you know, sort of a mismatch sort of a data. There may be sparsity. So you have to tackle all of that through the EDA. You also have to look at the data types. So report date should be date time. Again, this is something that's already been done previously, and these are correctly flowed, as you can see, for all of these. This time component column, which will obviously not require anymore, but this was added to it previously because of as an outcome of some of the analysis. So if I just describe it, this is how it looks like. 71, as I said, for each of the rows, 71 in number. And these are the different mean values for each of the values here. And the min and the max and the quartiles, the different quartiles, right? So you can see Google Ads impressions, for instance, it can go as low as 720, and this is probably because the data wasn't collected at that point. Okay, and that's why you see 11 in Google Ads spend. So there is outliers here in the minimum, a lower threshold outliers as well. And that's because the data hasn't been collected enough till that point. But I deliberately kept not just the extreme values like zeros, but also some outliers like this. These ideally should be eliminated from the data for proper analysis. All right, so I'm going to do a quick plot now. Now this plot is going to look like this. So we did a plot earlier, but this one is going to be like properly labeled and with the time stickers here in 45-degree rotation, as you can see, with sort of four kind of markers. And yeah, that's pretty much again basic Python code to do the visualization using matplotlib. And so we can see the trends here, and we can see that towards the end of 2024 there was a spike here in this position. Okay, so we saw that from around from around the middle of 2024, there's been an upward trend. Before that, it was relatively keeping steady. Right. So now we're going to do we'll see the monthly variation in the data. So now you can see in the uh, x axis we actually have the different months. So what we just sort of figured out. So see, that's the power of visualization. We obviously have to sort of guess what's around the month here. We can do it's not very difficult, but here you actually have it precisely. So in December there was an increase spike, as you can see, right? Did it happen previous year? Again, comparatively, yes. And since we don't have the historical data, it probably could have been lower potentially, which meant that it was higher in December compared to the rest of the year. Okay, so again, the more the data, that's why the more comprehensive the data set, the more the information, the more you can learn from the data, and more the algorithm can learn from it as well. But yeah, in this case, that's all we have from the November of 2023 to this one. So now what we're going to do is move into the first time series approach, and this time it's not profit. I'm going to compare it, and this is where we'll see the comparison. I'm going to compare it with a very popular autoregressive model, another time series forecasting model, which has been around for a while, and this is called SARIMAX. This is sort of an extension of SARIMA. Okay, so SARIMA is nothing but seasonal autoregressive integrated moving average, and that X stands for exogenous factors. So you can have some exogenous variables added here as regressives. And if I look at the structure, the way it has been used, you can see that there are, so you will see that it's a time varying regression, and you can see there are multiple factors which will multiple parameters, and all of these actually stand for the different lags. Okay, so it's lagged by one period for each of the components of SARIMA. So autoregressive, integrated, moving average, all of these are lagged by one. And then you have 12 months of seasonality. Then you fit the model, then you forecast it for 12 steps. 12 steps in this case would be 12 months. So that's how it works. Okay. And so now you can see that the output of the SARIMA actually looks good, right? It has got this little thing here, and which is somewhat resembles the kind of pattern that the curve has, that it has been able to pick up, but it's gotten revenue absolutely wrong. Like it was at the level of say 75,000 a year, but it's predicting somewhere around 40,000. So why is this happening? This is happening because it dropped massively to zero here. And that is the point that I was trying to make at the start, that Facebook profit has some advantages over these AI kind of models, or some extreme outliers. You can call this extreme outliers as well. And you have two of them, that makes it even worse, right? So it almost like it's a recurrent pattern. So it has got that, and it's sort of done this kind of internal averaging sort of a thing, and that's why it has, sort of done this weird kind of forecasting. It's saying that it's going to drop massively to around sort of the number. So that's where we can do this kind of comparison. Handling sudden drops, Facebook is much better. It adjusts dynamically. In terms of holiday and seasonality, it detects automatically as well. Again, so that's why I said, by default, Facebook Profit is already very robust. It can handle a lot of things on its own without you having to do too many manual interventions. But yeah, if you know stuff, and I'm going to give you some cues here in this video, I can do some stuff manually as well. It can model trend changes. It can handle digital values gracefully. All of these things are not as good in case of auto-regressive models. Obviously, Serena is not the only one, and there are others, like Arima and all, and each of these have their own merits as well. So it's not like a black and white thing. A lot of advantages and disadvantages are there. So yeah, each has its own merits. So it assumes data to be following a consistent pattern. If it drops to zero, it might interpret as an outlier strong approaches. Profit dynamically adjusts to trend changes and recover from sudden cost variables. Okay, now we are going to go into profit, which is our main topic for this video. So first of all, we have to prepare it, and for preparing we mean that we reset the index if there's been an index which has been set, and then we can choose two columns: report data and shop values on that. And internally, this is how it has to be renamed. So it has to be DS and Y. These are the columns in this particular data frame that we're going to use for profit. That's how it is defined within profit. That's how it realizes which one we're talking about. So DS is the one which refers to the time component, and the Y is the one which has the values. So now we are going to move into some implementation. The green ones here are the ones which can be done. I have used only this one, but I'm going to talk about the green ones as well. Alternative implementations. So this is where we invoke the model. This is creating an object or an instance of the profit model. And you can see end change points 25. We'll talk about all of these. Seasonalities, multiplicative, yearly seasonality, true. So first of all, you can define any kind of seasonality, custom. You can have daily seasonality false, yearly seasonality true. You can have daily seasonality true, weekly seasonality true, false, anything, right? So you can have multiple kinds of seasonality. Doesn't mean that it's only going to have yearly seasonality. You can have weekly seasonality as well. So you're already starting to see its sort of capabilities, its advantages, right? And you can do it so simply. You just have to use this word, daily seasonality. You also have to decide a certain uncertainty level. So any kind of model will have an uncertainty level, right? It's going to have an error margin. So you can define that error margin or a confidence interval, and this uncertainty interval is going to be by default to be 80%. And as you can see here, it's not been defined explicitly in this case, the way I've done this. Therefore, it's taking the default of 80%, but you can set it to 95%. You can do this using this called interval width, right? 0.95, which is 95%. For instance, if you go with 95%, which is a really big confidence interval, and that's the normal one, by the way. That's usually used. Suppose 0.05 of p value, that corresponds to 95% confidence interval. So by default, it will only return uncertainty in the trend and observation noise. But if you want to do it for seasonality, then you must do full Bayesian sample. So that's when it goes with the Bayesian thing, and that's why you have to provide prior information. This is done using the parameter mcmc.samples. So mcmc is the Bayesian approach and for sampling, and this is a huge topic. We'll probably take it up separately. I recently talked about it a little bit in my videos, which covered Meridian, the Google marketing mix modeling. and solution open source one, and NCMC stands for Markov chain Monte Carlo, or Monte Carlo Markov chain, and it's basically a method, a Bayesian method for carrying out sampling. So you can see 500 draws. That's one example implementation, not down here in this example, for instance. So you can have other kinds of custom seasonality definitions using something called a Fourier order. Okay, a Fourier order is like how many, say, for instance, how many peaks, how many changes in points there will be for defining seasonality. The higher means that there's a higher frequency. Okay, so it's like a frequency of recurrence of the seasonality effect. So this is how you can do the custom thing. We're going to look at Fourier order a little bit later, but I just wanted to show you upfront, what are the ways of doing the customization. So then you fit the model with the data. Remember, this is the data that we created, and then we have then we go into the forecasting. So this is where you actually do the forecasting. Okay. So you have your existing data frame, but on top of that, you're going to decide, okay, 20 periods into the future, which is 20 weeks into the future. Remember, this is a weekly data, so anything we define here ideally should be in weekly. Okay, otherwise it looks weird. It's not, it's going to be confusing. So the frequency has to be defined. So W here means weekly. It could have been M for monthly. So we're gonna see forecast 20 weeks into the future, and then we're going to do a model prediction. Then we're going to also plot the forecast. Okay, which is done by model.plot forecast. And this is how it looks like. This is the first time you're seeing what it actually does. Let's quickly look at what this is doing. So first of all the black points here, those correspond to the data points for revenue. And you can see there's a shaded region. This shaded region is actually that interval width. And you can see it has done a brilliant job. Most of the black data points, almost all of them except these two here, are actually within the shaded regions. Okay, it just misses out on this one here, and that's because of this major drop here. And you can see this is part of the forecast. And this is what I was saying about Facebook profit. Remember what happened to Serena? It completely got it wrong, right? It suddenly totally lowered the baseline and said that, okay, this is around where we think this could be around. Of course, again, this can be probably fixed as well, even with Serena, but this was a relatively simpler implementation of it. And that's what I wanted to show, that even without going too deep with Facebook profit, without a very complex implementation, a relatively simple version of it can actually still tackle these problems of extreme outliers. Ideally, you should not have this kind of things in your data set. That's just bad data science work. So you should definitely get rid of this kind of outliers, but I just wanted to show it and therefore kept it in. But you can see it tackles it gracefully. It of course lowers the prediction here massively, but then it sort of gets back into the into the groove, and you can see it fits in very well with the data. So by the way, what I've done here so far is only use the entire data, okay, for the forecasting. Ideally, what you should do is sort of spread it out. So there's no way for me right now to actually validate this because this is future data, right? This is not even there. I can't compare it with anything. So ideally, what you should do, and I will probably show it in a future one, is to split it up into train and test, meaning that we will have, say, 80% of the training data and 80% of the original data for use for training, and then 20% for testing purposes. So that becomes your unseen data, your future data that you're trying to forecast. And then you sort of compare the values and compare, calculate the errors. So that's like a more robust technique. Ideally, that's what you should be doing if you don't have future data already. But then that's just for like practice or exploring. Ideally, what we'll always do is focus for future. So why you should do that is to train a model to actually see what the model is doing. Is it really able to forecast well? But obviously, you will always apply it on unseen data, future data for which you don't have the original data yet. So yeah, this is the interval width, and you can see that for the data here, this is the prediction levels. These are the black points, which are the original ones, and this is the forecast, of course, the blue line. And you can see it's done a pretty good job, right? It has got the black points, all the original data points nicely within the interval width. So nice job there. If you want to reduce the interval width, some of the black points might actually be outside it. But yeah, that's going to make it a tighter, so right. So you can actually see the different forecast values here. So y hat is your forecasted values, and you also have the interval width given here by the upper and lower values. And then you have another thing which is pretty cool with the Profit. You can actually see the components. So this is the trend component. Remember what I said at the start, the time series always has these three components, which has the trend, the seasonality, and then the residuals. You can add them back together to get the original time series data. So this is the trend here. This is an upward trend like you saw. Yeah, it's pretty linear. And then you actually have the yearly sort of seasonality, and it kind of repeats. So the reason why we don't get too much yearly seasonality is because this data set doesn't have yearly data yet. I mean, it has got like 16 months of data, but um, I mean, if we have longer periods of data, like several years, like say 5 years, then we will be able to actually see how it varies on a yearly basis. So right now, that's just not possible. So now, yeah, so now we're going to come to another cool thing that Profit has the capability of doing. Again, this is not a concept that's unique to Profit, but it does allow its incorporation. The concept of change points. So by first specifying a large number of potential change points, so change point is nothing but the points at which some major or some noticeable change in pattern in the data happens. That's pretty much what it means. So it identifies the number of potential change points at which the rate is allowed to change. And it then puts a sparse prior on the magnitude of these rate changes. Okay, means that it sort of predicts. And this essentially means that Profit has a large number of possible places where it can change. But it thinks it can change, but it should only use a few of them. So if that's confusing, that's fine. But the idea is to understand that it's just trying to predict where the changes happen. And it's basically like understanding that if this is changing this way, then it's changing, then it's changing direction in this way, and that's how the ultimate outcome is right. That's how the forecast is done. Okay, so this is of this is actually from the documentation itself. This is the example of change points from the Profit documentation, and I just use this code here to take this image from the documentation itself, just represented it here, and you can see that this is these vertical dotted dashed lines here, rather. These are the change points. In this case, it's pretty equidistant, so it sort of predicts that. And you see that this is a very simple data set. That's one of the reasons why it's relatively more complex in our case, right? If you look at the kind of graph that we have, right? Real data sets are more complex. This is a one which is probably, which either was a real data set, which simply by its very nature was much more stable. And you can see it's relatively very stable data, right? Just visually also you can see that, and that's why no wonder that if Profit figured that the change points are going to be very equidistant from one another. Now we apply this in our case, and in our case, what I did here was a little unconventional. I had to actually manually also include the change points. Um, so for some reason it wasn't actually showing. So if you have got any ideas about that, you can let me know in the comments. But yeah, I had to sort of manually verify if it was not there, then sort of go ahead and add it. These are the dashed lines. And you can see this forecast here remains the same. This is the same one here. But in this case, we simply have the different change points. And why is this important? Okay, and you can see first of all that they're not necessarily equidistant. In this case, it's increased, right? So okay, reconnect. But yeah, so why is it different here, or rather, why is it important? Why do we need the change points? And by the way, it covers like 80% of the data set. Okay, almost. That's how it goes. Even in this example, you see it's not the entire one. It's 80% of the data set that's covered by change points. So it's important because we can actually define it. So we can say, for instance, if we go back to the implementation, we'll see that the number of change points was 25. So we can tell the model how many change points to actually give in order to give the model the direction about how many times it changes in the data set. Okay, the value changes. That is, if we have prior information regarding that, if we know that, okay, there are going to be, these many changes in the data, because we have some information which is probably not reflecting in the data set somehow, or just to make it easier for the algorithm to pick it up. then we can provide that. Okay, so that's the customization. Not only that, okay, this is only where I've shown you the number of change points. You must have offered to you, hey, how does it now? What is the method of actually telling it the exact location where this is going to happen? Not just the number of times, but the exact location. We can also do that. So for that, you will have to jump into the documentation. So they have a very good documentation on the GitHub.io page. You can take a look at that. Okay, so you can go for custom seasonalities, and that's going to give you, you know, the implementation for that as well. Okay, change points. You're gonna have to, yes, you can give specify the location of the change points. This is what I was talking about. So you can jump to that part, and you can specify the change points like this. You can tell that, okay, this is where the change point should be located. All right, so you can do that as well. Great. So by the way, it can be implemented both in R and Python. So if you, in case you're, trying to give this a go, get your hands dirty with it, playing around with it, you can do it in R also if you're familiar or more comfortable in that language. So now we're going to, yeah. So this was our implementation on our data set, and in our case, we have implemented 35 of them. Okay, so if we actually look at the change points here, we can see that by just doing modular change points. This is our implementation called not the profit model, and these are the 25 points. You can see these are not all the points here. So we're missing, of course, all the change points. 25 of them, 25 of them are listed here. So then we can do something else, and this is called the diagnostics. So if you go into the documentation, they have this part here called diagnostics. So this is where you're evaluating how well the prediction is really doing, right? And so that's one aspect of it. The other aspect is to also look at how well the choice of change point is doing. Okay, so that also can be validated. That can be validated by considering number of change point values and seeing which one is doing better. And that is done by something called a cross validation. So I'm not going to discuss in detail what that means. But cross validation simply means that you're taking part of the data and using it for testing and seeing how well it is doing in terms of forecasting. Okay, I'm going to do it repetitively, and in this case, repetitively also iterating also over the number of change points. So that's why we have a for loop going on here, and we're going to see the cross validation. Let's see the underscore CV, and we have some parameters here. So we're going to have to give an initial number of days, which is going to be the training period, basically. So that's the training window. Then you have a period, which is the step size for testing, which is 35 days, and horizon, which is the forecasting window. Okay. Now, there's some thumb rules for that. So the step size testing, this ideally should be at least like 10, 15%. Okay, and then you have, so the reason why it's called step size is because it's going to do in batches. Okay, so it's always going to retain some of the previous um, part of the data for doing the next analysis. So that's why it carries it out multiple times. Now, like I said, 10-15% should be there, and the initial number of for the testing for the initial, which is the training window, the initial should be like quite a few times, X number of times at least the price. So that's the kind of thumb rule that's been using coming up with these numbers. But again, this is not set in stone. This depends on a lot of things. Let's look at the performance. So RMSE is root mean square error. So this is what's going to give you the evaluation. So this is like an error measurement to try and understand how well it has minimized the errors. The objective of any of this kind of evaluation or diagnostic methods is to sort of minimize the errors and see for which of the cases the error is minimized most. So it is, once we run through this, it's going to carry out this analysis, as you can see in the back end, changing, testing for different change points, and finally it comes to the conclusion that okay, it's 50 is the best one. Okay. So there you go. So instead of providing a list, by the way, you could also provided a range. So you could have done, a range of tests, or you could have, done it for a range, but that would have taken very long, right? So that's also something you have to keep in mind. Remember, there's a computation cost involved, right? Yeah. So compute units are often going to be consumed here, and you might have to pay for it. Okay. So profit by default will fit weekly and seasonality, yearly seasonalities if the time series is more than 2 cycles long. So It will also fit daily seasonality for a sub-daily time series. What it means is that depending on the granularity of your data, it's going to try to find seasonality at the next higher level, the next higher order. So if it's sub daily, suppose it's for different hours, it's going to try to find seasonality at a daily level. If it's multiple months spreading over say 30, 40, 50 months, that's going to try to find yearly seasonality because it's not taking it. So that's by default it's capable of doing that. This is pretty cool. But you can also add other seasonalities. Remember what I just showed. You can define the number of seasonalities. You can give a Fourier order for that. And that Fourier order is what defines the frequency of the seasonality. So for default by reference, by default, Profit uses the Fourier order of 3, weekly seasonality, and 10 for yearly seasonality. This is not cast in stone. You can change it. And the higher the Fourier order, the more the flexibility to capture complex seasonality. The lower the Fourier order, it's a relatively simpler seasonality pattern and it's less prone to overfitting. But yeah, if it's too low, then it might mean that you're not able to capture the seasonality properly. So this is where again a trade-off exists. Now we're going to look at a second version of the model here. And this is where we're going to look at the implementation of Fourier order. Okay. In the previous version, remember we did not use this. Let's go back to the code where we did it. Yeah. So we did not have the Fourier order here. In the green ones, which are not used, were commented down. It was being suggested. So this is the part where we actually use in the second model, second implementation, just another version to show you where we're using a Fourier order to give a custom seasonality. And this is an example of holiday. Okay, a very simple one. We're going to look into the documentation just quickly to also see how we can implement holiday effects better. And with holiday effects for the frequency of weekly 12 weeks into the future, this is what it looks like. And you can see that this actually handles the spikes better. Okay, because of that Fourier order of 10. So if you look at this curve here, it actually figures out the spikes really well. If you look at all the spikes here, it is beautifully capturing most of the spikes. The interval width remains the same as before. It's not been defined, so it remains at 80 by default. But it very nicely, finds out the spikes. The only thing that has happened here, you can see difference, is because while it's trying to do that, it has actually failed to capture all the data points, which are the black points here. Some of them have now gone outside of the shaded region. Okay, so that's what's happened. So that's the trade-off. So there's always going to be some aspect which is not better, right? And if you look at the previous one here, all these were very tightly fitted within the shaded region, within the interval width, but it did not capture any spikes as much. But if you look at these spikes here in the prediction, see it's actually trying to predict the spikes. So that's the simpler way of incorporating custom seasonality. There is a more holistic way of doing that through modeling holidays and special events. By the way, there are some built-in country holidays as well. Okay, and you can invoke those. I'll just show you. So you can invoke those in Python in this way. So you have to give the country name and then you just add the country holidays. Okay, so that's also something you can do. So in Python, if you have to do custom seasonality, you will have to create a data frame for each of them. And we'll have two columns, holidays and DS. DS, remember, is the time one. And you also have to give two columns for the lower window and the upper window. So this simply means that suppose you also include Christmas Eve along with Christmas, you should include lower window is equal to 1. Then if you have Black Friday, which occurs after Thanksgiving, then which is a later thing. So that's why the upper window is 1. All right. So this is how it is done. This is how it's defined. So there are a couple of data frames here, as you can see. And first you get the name is holiday, Super Bowl, holiday playoff. Suppose a sporting event where you can have an uptick in those sales numbers. So you can incorporate that. The reason why I haven't done it in this implementation, by the way, is because right now I haven't yet collected enough information around that yet. How to incorporate that, but probably maybe a future implementation will show that as well. Time permitting. So yeah, you can actually define the dates, as you can see. So you can define the dates in the DS column, like I said, which corresponds to the time component, so as to where these should be applied. Okay. So that's how you implement the custom seasonality. There's a lot going on here. You can actually see how the forecasting is looking like for each of the time components. So you're basically adding it all up. So forecasting of playoff, forecasting plus the forecasting of Super Bowls. Only the absolute greater than zero, meaning that you're taking the absolute value. So it's essentially non-zero values, and then you have these columns here in the last rows. Okay, so there's a lot going on here in the documentation. Do give it a look. It's very difficult to cover everything. You might not require everything. It's discussed for your order, specifying custom seasonalities. So all of these things are here. So there you go. This is what we have already seen in an example implementation that we saw. This is a monthly one, by the way. It's just taken roughly average figure around the entire year. There's like roughly the number of days in a month, and a Fourier order of 5, right? So remember, it's a Fourier order of 3 for weekly. I think somewhere in the documentation they mentioned it. So usually a Fourier order of 3 is taken for weekly. So it's just taken a little bit above that. Yeah. So I think that's pretty much it. So let's break down now quickly the difference between the two models. So this was the model that we just spoke of, where we have used Fourier order to have a custom holiday implementation for a holiday effect. And then we had another model previously, remember, we didn't have that. So the main difference here is that it suggests the presence of an event repeating every 12 months. And you have a custom seasonality that's getting added. It helps capture the spikes, and it learns complex seasonal patterns, so on and so forth. So this is the implementation. This is what I wanted to show you. Like I said, spend some time on the documentation. Then you can use my video. If you want, I can share the notebook. And you can do so much stuff with this, right? You can try out multiple ways of forecasting. You can have different kinds of custom inputs to it. But even if you don't do that, if you're not too familiar with it, you can still get started with the basics and actually do a lot of implementation yourself and do the forecasting. This is a good time to do it. Go ahead and do it at this time of the year, so that the rest of the year you will have the numbers to sort of use as benchmarks. So I hope this was useful. If you have any questions, do leave them in the comments below. And